the academic development programs are such that you cannot get the other four things in this particular program. You will get the glimpse of it. Just to start with. Say that those who are doing intake or those who are studying PhD, this is the starting of the research. So if your foundation is able to take the bridge over that foundation,
I know that you are at the fag end of the training program, so you must have been exposed to these tools to a great extent. But what I will try to do is that try to give my own flavor to them and see how you can appreciate these tools to such an extent that even if you haven't focused on these tools for the last 5 days, if you focus on it for now, for about 1 or 2 hours, you should be able to appreciate what you can do with these tools. Am I okay? Am I audible to you? Yeah. Okay. Is there a slide changer? It's okay. Otherwise, I can use this keypad. Yeah. So what I would like to do for the maybe with some break, what time I need the schedule? What time is the break that you want to have? After 1 hour? Yeah. Say around 11:15, 11:10. Yeah. So my presentation will be there up to 12:30. Yeah. Yeah. 12:30. Yeah, correct. Okay. So I'll pause around. No problem. And no sedimentary rocks in between. Actually, I always tell in my class that I try to make my presentation at my pace. Okay, but if you want it to be at your pace, what you should do is you should stop me and ask me some questions. Okay, then I will slow down and go at your pace. Okay, so what we'll try to do is to learn these 3 important tools and see how they can play a big role as far as water resource assessment is concerned. Remote sensing, basically to estimate the land use and land cover changes, and GIS for watershed delineation, among many other things, stacking of database and other things, and DEM for drainage pattern estimation. I just wanted to check, DEM was exposed to you, digital elevation modeling? Okay, yeah. So again, okay, okay. Maybe I'll try to show that again with some details, okay, and try to use all these 3 tools in one particular hydrologic model called AV SWAT and see how we can try to assess water resources of a given river basin. Now, as I told you, what I will like to do is that to go slow, okay, and explain these tools again. It's like, you have already learned them and relearn them. We use one more terminology in our institute. When a student joins us, we tell them that first of all, we have to make sure that he unlearns what he has learned so that he can come back to what we want him to learn. Okay. So here, these tools I'll briefly expose, and then we'll try to talk about their utilization. Okay. So first thing that we want to talk about is remote sensing, and one important aspect that we can get from remote sensing is synoptic view. Means a large area can be covered in one image, and that gives a huge asset as far as our natural resource assessment is concerned. Just to give you an idea, what you are seeing here is entire India and its surroundings shown in one image. To be frank, it is not just one image. There are multiple images there, and what we are seeing is the digital mosaic that you can make out from seeing that this portion of the image. This pointer is visible. Pointer is visible now. Yeah. Otherwise, I will move here, and you can see that there is one path of the satellite like this, another path of the satellite, and so on. Okay. There are multiple satellite images that were put together, or even a physical pointer would do sometimes. Yeah. So Yeah, it comes sometimes, it's not. Yeah. Maybe I'm moving the mouse very fast. I don't know. Okay, so all these, there are multiple number of images, okay, and using all those images, we prepared what is known as digital mosaic, and that mosaic is now comprising of the entire India and its surroundings. And I think you might have been exposed already. What you are seeing in red color here is actually healthy vegetation. Okay, this is because what you are seeing is standard false color composite. Now, if you know this portion, bear with me. I'll again try to explain why we try to give this kind of false color composites and other things. As far as remote sensing is concerned, we try to do it for a very large, wide spectrum of wavelengths, and that when we want to talk about, we call it as basically the EMR spectrum, okay, electromagnetic radiation, basically from the source, whatever may be the source of the light, from that source we have one electric wave and one magnetic wave, and these two are perpendicular to each other, and those two, EMR itself is orthogonal to the source of the light. And if we talk about a wave like this, electromagnetic wave, we try to express that wave either in terms of its wavelength, that means the distance between two peaks, or frequency, the number of waves passing per unit time. Okay, and if we know one, we know the other. They are inversely proportional to each other. Okay, so if we talk about the wavelength and frequency, they are inversely proportional to each other. Let's say wavelength is lambda and frequency is f. The proportionality constant is called c. C is wave celerity, that is speed of light, that is 3 into 10 power 8 meter per second. Okay, now that is known constant, proportionality constant. Therefore, if we know frequency, we know what is the corresponding wavelength, or if we know wavelength, we know the corresponding frequency. And as far as optical remote sensing is concerned, we always express the remote sensing terminology in terms of wavelength, knowing very well that we can use this equation to convert it into frequency. Okay. So if we talk about the EMR spectrum, depending on the wavelength, we have various waves that are available to us with different wavelengths. If you look at the entire EMR spectrum, okay, this is shown on a logarithmic scale here. Okay. What you are seeing is that 1 unit here is 1/10 power. Okay. So starting from somewhere around 10 power minus 8 up to about 10 power 9, we have wavelengths available. And if you talk about 2G spectrum, 3G scam, 4G scam, etc., all of them happen in this region, okay, for mobile communication. Right? Now, in this entire EMR spectrum, if you focus on, these units that we are mentioning for as far as wavelength is concerned is micrometers. Okay, so that being the case, if we talk about the small hashed portion here, this is between 0.4 to 0.7 micrometers. Okay, and that is zoomed here, and you can see that 0.4 to 0.7, that is the visible region. That is the only region of the EMR spectrum for which human eye is sensitive. We can't see anything outside this region. Only in the 0.4 to 0.7 micrometer range we can see the energy. Other portions we can't see. But we have sensors which can see. For example, you might know about X-rays, you know about ultraviolet radiation, which is used for physiotherapy and things of that kind, right? So they're all available. There are sensors which can do it, but we can't see. Problem is that what we can't see, we want to see. And for that, what we try to do is that we try to give some false color to that and prepare false color composites. And that's how we use these 3 primary colors called RGB, red, green, and blue, okay, and try to use any 3 wavelength regions and give them RGB, prepare a color composite out of it. Among them, you get one true color composite. That means take the blue band and give blue color, green band and give green color, and red band give red color. That is your true color composite. Any other combination, even within visible region, for example, you take a red band and give it a blue color, okay, a green band, give it green color itself, and for blue band, give red color. We are within visible region only, but we are manipulating the colors, right? And that produces a false color composite. More importantly, what happens is we just go beyond this region, near, infrared region, starting from near infrared, middle infrared, and thermal infrared. Okay? And those regions, when we have information available which we can't see, we try to give some color to it and produce a false color composite. Typically, when compared to the visible region, if you try to use a portion of the visible region and infrared region, we get a lot more information than what we typically get only in the visible region. That's why we try to use false color composites. And English literature wise, it may be wrong to say that first of all we are saying false color, okay, and then we say standard false color composite, okay, and the standard false color composite is the most popular color composite that is used to do lot of interpretation of satellite imageries. Now, in that context, since you already know or you have been exposed to this, I would like to focus on these 4 important characteristics of remote sensing, which play a big role. And if you try to use any satellite imagery, or for that matter any imagery, you must keep note of these 4 important characteristics: spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. Last one is only common as far as satellite remote sensing is concerned, but the first 3 are for any remote sensing platform. It may be satellite, it may be aerial, it may be ground based. Everywhere we can talk about the first 3 characteristics, and the 4th one is specifically for satellite remote sensing. I'll try to explain each one of them, even if you know a little bit. I'm sure you know already, okay, but explain them with some simple examples and show why it is important to understand each of these characteristics and appreciate their use as far as our water resource assessment and management are concerned. Okay. So if you talk about first one, that is spatial resolution, what we are trying to do is, that we take a small elemental area on the ground. Typically it will be a square box, okay, and that entire square box is observed as one dot on an image, which is also called in your mobile terminology as a pixel, right? I don't know, nowadays when you purchase a mobile, you will never purchase a mobile to talk about how good it is in communication. You try to purchase a mobile based on how good is the camera on it, right? And also what you say is that, what is that camera storage? Is it 3 MPa, 5 MPa, 10 MPa? You will be willing to, even if you see iPhone advertisement, it's an iPhone advertisement, but they will try to show you picture taken from iPhone as the advertisement, right? So they give so much of importance to that, and that pixel among the megapixel, mega is 10 power 6, right? So among the pixel, one pixel, what it is representing on the ground is referred to as spatial resolution, and typically it's a square box. So if I say that the square box size is 10 meters, that means 10 meters by 10 meter square box is 1 pixel on the image. So that pixel on the ground is covering 100 square meters, right? So the smallest elemental area over which we make an independent observation is called as spatial resolution, which is expressed as a square box and typically expressed in meters. And if you say that we have a very fine spatial resolution, that means the box size is very, very small. And we have very coarse resolution, that means the box size is very, very large. You may have a satellite sensor which may give a pixel or a spatial resolution of 1 meter to some satellites which may give a spatial resolution of 1 kilometer. Okay. And just to give you that, drive that point home, if you look at this image here, there are 2 images that are shown here. On the left hand side, what you are seeing is an image with a coarse spatial resolution. Okay. And you can see that large area of a city and surroundings are shown in this image. Okay. Whereas this image at a very fine spatial resolution, okay, it is just picking up a small portion of the city, one small layout, urban layout, to such an extent that you can see the rows of houses here, okay, and you can see a car parking area and a car coming into the parking area and things of that kind. So with increase in spatial resolution, we get lot more detailed information of any given region of our interest. Okay. I'll just share one small joke with you on this. When we were talking about increasing the spatial resolution, those days they used to say the 30-meter spatial resolution is excellent. Okay. But now if you talk about, you have 1 meter resolution, and now we have sensors which we call them as sub-pixel or sub-meter spatial resolution, means less than 1 meter spatial resolution, you can try to get the imageries. We had, when we are talking about 30-meter spatial resolution, we had one Russian scientist from Russian Space Agency came and gave a talk in NRSC, and he was telling us that if an American soldier eats banana, okay, and after eating it, if he throws out the leftover, we can pick it up on the imagery. That's the kind of spatial resolution that you can think of. Okay. So that's the kind of spatial resolution that is available, which is a big deal and has very important role as far as the water resource is concerned. Just to drive that point home, in this image, okay, you can see a large number of imageries in this slide. Okay, I can tell you that there are about 20 or more than that number of imageries that are there in this slide. Okay, look at this first slide, first portion of the image. Okay, this is from one particular satellite called MODIS, nothing to do with our Prime Minister Modi. Okay, it is moderate imaging scanner onboard Aqua satellite. Okay, and this sensor has a very coarse spatial resolution and it has a very high temporal resolution. I'll explain that. Okay, so if you look at it, it is covering a large area, roughly about 1200 kilometers by 1200 kilometers. So it's like entire Ganga basin and its surroundings are covered in one image here. Okay, now within that, look at this small yellow box. Okay, it is roughly about this is 1200 kilometers, so it is about roughly 1/6 of it. Okay, so it is just covering roughly about 200 kilometers length and 200 kilometers width. So that yellow box itself is this image. Okay, and this is from Landsat ETM Plus. ETM Plus stands for Enhanced Thematic Mapper Plus. Okay, and that sensor has a very good spatial resolution when compared to MODIS. So if you talk about this, it is only 1/6, so it's about roughly 200 kilometers by 200 kilometers. So what you can see in this yellow box, you can see with a lot more clarity in this imagery. Okay, now if you want to cover this entire area at this spatial resolution, okay, this is 1/6 of it, therefore you will require 36 imageries to cover this entire area. Just to give you an idea, typically whatever may be the spatial resolution, an imagery costs about 25,000 rupees. Okay, so if you don't have much money, just go for one image to cover this entire area, 25,000 rupees, you are done with it. But if you have a lot of money, then go for 36 imageries into 25,000 rupees, then you can cover that same area with very high spatial resolution, right? If you have more money, then what you can do is look at this small portion, this yellow box. This is roughly about 1/10 of this image length. So if it is 200 kilometers, it is roughly 11 kilometers. Okay, so this yellow box itself is this imagery now. Okay, this is from a particular satellite called IKONOS. It's a Greece satellite. IKONOS, and Greece means eye or human eye. Okay, that's a sensor, and that has a very high spatial resolution, and you can see that this portion is now an image here. Okay, and if you further take this yellow box, and you can get it only about 1/10 of it again, so 1 kilometer, and this is a spatial resolution at which we can try to cover this entire area. As I told you, if you want to now cover this entire area at this spatial resolution, okay, first of all 36, okay, and this is, you require about 100 here, 1/10 of it, so 100. So 3600 imageries into 25,000 rupees. And if you have that money, go for it. You can cover this entire area at that spatial resolution. Why it is important as far as water resource is concerned? If you want to do river basin planning and management, okay, an entire river basin like Mahanadi Basin or a large river basin and its surroundings, if you want to talk about integrated operation of the entire basin, okay, then maybe at this spatial resolution, image would have been sufficient. But within that basin, like you want to talk about one small tributary like Yamuna or much smaller tributary, and you want to focus only on that portion of the basin, then this spatial resolution is good. Okay? But then let us say that you are not even interested in such a tributary, but you are only interested in our Prime Minister's constituency, Varanasi. Okay? It's a small portion of the imagery. Then we can try to go for much finer spatial resolution. So for river basin hydrology, to watershed hydrology, to urban hydrology, we can think of going for various spatial resolutions. Okay? And depending on that, we can think of what particular type of sensor that we should use as far as our hydrologic assessment is concerned. So starting from very coarse spatial resolution up to fine spatial resolution, we can go, and it will have very serious implication. That's one aspect, that is spatial resolution. The next one is spectral resolution. And this one, I had told you already that you looked at the entire EMR spectrum, that on a logarithmic scale, okay, somewhere around from 10 power minus 9 micrometers up to 10 power 9 micrometers. Such a large, wide spectrum. In that, if you try to choose one small, narrow bandwidth, say 0.4 to 0.5 micrometers, okay, that is one spectral band. Okay, and that we call now as one band, and bandwidth is 0.1 micrometers. And if you say that 0.4 to 0.7 is my bandwidth, that means 0.3 micrometers is the total bandwidth. Okay. Why I am referring to 0.4 to 0.7 so much is that is actually the visible region. Human eye is sensitive to that. Okay. And if you try to do the remote sensing in the entire 0.4 to 0.7, which you try to do typically when using your mobile, if you take a picture, okay, it's basically using the entire 0.4 to 0.7 micrometer bandwidth. Bandwidth is 0.3 micrometers. Okay, and that in remote sensing technology is called as a panchromatic image. Okay, panchromatic image has a very important role to play, but one disadvantage that we may face is, look at this image here. Okay, there is one feature called A, and there is one, if you look at this feature here, the reflectance is, if you try to look at this entire 0.4 to 0.6 micrometers, okay, it looks like one feature is like this, feature A, and another feature is like this. What I am showing is on x-axis the wavelength, and on y-axis I am showing the reflectance, which is converted to digital number. Okay. Now, if you look at this, the average reflectance in the entire wavelength, if you look at, it will be same as what you have for this feature. Therefore, if you are trying to do the remote sensing in the entire range of 0.4 to 0.6, you will not be able to distinguish this feature from this feature. Both would look exactly same. Whereas, if you try to look at 0.4 to 0.5 as one bandwidth and 0.5 to 0.6 as another bandwidth, what happens is this feature has only this much dn, whereas this feature has much higher dn. So you will be able to distinguish. In the same way, again, this feature has this much dn, whereas this feature has much lower dn. Again, you will be able to distinguish. Advantage is, if the narrower the bandwidth, there is scope for you to distinguish two features which may look alike over a larger bandwidth. In that context, we try to talk about the spectral resolution. So again, take this 0.4 to 0.7 visible region. Is the entire region, if you try to take as one band, 0.3 micrometers bandwidth, okay, you will get one image like this. Whereas, if you divide this into, let us say, 3 bands, each of 0.1 micrometer bandwidth, blue band, green band, red band, then you get 3 images for the same region but in 3 different spectral bands. Okay? And if you want further, you can divide this into 6 spectral bands. Bandwidth has reduced now to 0.05. Okay? 0.4 to 0.45, 0.45 to 0.5, etc. Okay? So you get 6 imageries for the same region, and the number of boxes that you see here will depend on the spatial resolution. Okay? Assuming that the spatial resolution is same for all these bands, you are seeing the same 3 by 3 size box. Okay? And the number of bands is very important here. Our remote sensing technology has grown to such an extent that we have now developed sensors which can do remote sensing in a very narrow bandwidth. Okay? So here you can see that 6 spectral bands are available. Typically, such kind of remote sensing is referred to as multispectral remote sensing. Multispectral bands, and try to do the remote sensing, multispectral remote sensing. And compared to that, nowadays we have the technology to divide this small range of 0.3 micrometers into about 100 spectral bands. So bandwidth will be measured in nanometers. Okay? And they are called hyperspectral remote sensing. There are already satellites which are doing that. One of the first satellites from NASA to do hyperspectral remote sensing is Hyperion. That is the first satellite. It is now not operational, but there is one Italian satellite by name PRISM, which is now doing remote sensing under hyperspectral remote sensing. What happens is this entire bandwidth is now divided into 200 spectral bands. But ground-based remote sensing, if we try to divide this 0.4 to 0.7, just 0.3 micrometers, okay? If you try to divide this into 1000 spectral bands, then it is called ultra-spectral remote sensing. This is available through spectrophotometer on ground or in the lab, but as of now, it is not available on aerial or satellite platforms. But hyperspectral remote sensing is already happening. In case if you have heard about Chandrayaan mission, okay, Chandrayaan-1 itself had a payload of HISIS or hyperspectral remote sensing. It had within visible region and near infrared region about 70 spectral bands. Okay, and that information was utilized, one of the sources to identify that there is water on moon. Okay, so these hyperspectral remote sensing plays a very important role. Just to drive that home, as far as spectral resolution characteristics are concerned, I am showing you here visible and infrared region from Landsat, each spectral band and the image, same area, but how it looks like in each of those spectral bands. Starting from visible blue, green, red, then near infrared, middle infrared, thermal infrared, again middle infrared. Okay? These are all different wavelengths. And if you look at the spectral resolution, which is measured as micrometers of bandwidth, okay? Here the spectral resolution is 0.07, and here it is 0.08, okay? And here it is 0.06. It is not uniform. Whereas here I have shown uniform bandwidth. Okay? Why it is not uniform here is that the signal strength available in each wavelength is different. What we want to do when we go for multispectral remote sensing is that we want to maintain almost uniform signal to noise ratio. So where the signal strength is very good, we can go for a narrow bandwidth, and where the signal strength is very poor, we go for a broad band. Okay? So here the bandwidth is about 2.1 or 2.2 micrometers, whereas here it is just 0.07 micrometers. Okay? That's how we try to do multispectral remote sensing. Each bandwidth need not be the same. Okay? And these imageries will be extremely useful as far as our natural resource monitoring is concerned. And again, to talk about coarse spectral resolution versus fine spectral resolution, if you see these imageries, on the left-hand side, you are seeing a coarse spectral resolution that is about 0.4 to 0.7, 0.3 micrometers, which is actually called as pan image or panchromatic image. Okay. When compared to that, what you are seeing is that visible region itself is divided into multiple spectral bands, and you are seeing a false color composite with multispectral information, very fine spatial resolution. Okay. Both are possible. That is one more important characteristic that you should keep in mind, spectral resolution. Next one is called radiometric resolution. Okay. When we talk about radiometric resolution, what happens is when we get the response or the reflectance to the sensor, okay, how well you are able to divide that into various digital numbers. Okay. For example, if we say that I only know that there is reflectance or there is no reflectance, binary system, 0 or 1. Okay. 0 means no reflectance, 1 means there is high reflectance. Between them I can't distinguish. That is simply called as 1-bit data. Okay. 0 or 1. So the radiometric resolution of that particular sensor would be 1 bit. If you have 2-bit data, you will be able to store 0, 1, 2, 3, 4 different levels. Okay. So 0 is your black, 1, in that case 3 will be your white. And if you talk about a 7-bit data, 128 different levels, right, are 0 to 127. So 0 is your black and 127 is white. Between that you have so many different values. Why it is important is that small reflectance that you are getting, you are able to resolve it into 128 different levels. Okay. Just to drive that point home, what you can see here is that this is black, this is white. Okay. And if it is a 1-bit data, it will be stored as 0 or 1. Okay. And if it is a 2-bit data, it will be stored from 0, 1, 2, 3, 4 levels. And if it is 8-bit data, it will be 256 levels, so 0 to 255. Same signal, if you are talking about 10-bit data, then you are able to resolve it from 0 to 1023, more than 1000 levels. That reflectance value you are able to decipher. The major advantage is that small variation in the reflectance you can try to identify, therefore you can try to distinguish. Major advantage again is that if you have one particular crop, let us say paddy, okay, in one place paddy is growing very well, and in another location paddy only, but is not growing well, maybe because there is no water or there is some amount of stress as far as water is concerned or pesticide is concerned. Because of that, the plant is not growing well. There will be a small difference in the reflectance. And that small difference in the reflectance can be captured if you are having very high radiometric resolution versus very coarse radiometric resolution. Okay. I'll give you some examples also. If you see here, okay, typically our Indian remote sensing satellite tries to provide imageries at 7-bit radiometric resolution, that is 128 levels. Okay. Whereas 1A, 1B, 1C, all of them try to provide the information at 7 bits. And if we talk about Landsat TM, which is also freely available, okay, it talks about 8-bit data, that is 256 levels. There is one satellite which tries to provide the information at a very high radiometric resolution, 11 bits, 2048 different levels. The sensor name itself is AVHRR, which stands for Advanced Very High Radiometric Resolution. Okay. And this is one of the best satellites as far as radiometric resolution is concerned. This satellite, which is available through NOAA is a subsidiary of NASA, National Oceanographic and Atmospheric Administration, and this satellite at 11 bits, data that is available is so good as far as 1 pixel is concerned. Okay. But the pixel size, if it is small, signal is weak, so you will not be able to resolve it into so many number of levels. So what they compromised is that the pixel size is very, very large. Spatial resolution of NOAA AVHRR is 1.1 kilometers. 1.1 kilometers. Okay, but the signal that is available is resolved into 2048 levels. So small variation agricultural condition or crop condition can be very nicely captured, and as a matter of fact, NOAA AVHRR data was used from 1970 up to 1990 to talk about agricultural drought in our country. Entire country, okay, NOAA AVHRR data was extensively used. There are important issues there. Spatial resolution is coarse, 1.1 kilometers, but the radiometric resolution is excellent, 11 bits. Okay, and this satellite data is used to such an extent that we used to talk about agricultural yield production also using this data. Again, I'll try to tell some story about it so that you'll remember this. Okay, you know what they used to call as Cold War regime between America and Russia, right? So this is a American satellite, NOAA AVHRR. Okay, Russians also might have had that similar kind of satellite. Okay, so during Cold War regime, for everything, America and Russia have to compete with each other, right? So what they used, this NOAA AVHRR data they used during the crop season and found that Russia is going to have less amount of wheat production at the end of the season when compared to what it would normally have through NOAA AVHRR. Okay, then they thought they now can capture Russia. Okay, so what they did is they stocked their wheat. Russia needs wheat because its production is low, so it has to import. Okay, and America has jacked up the prices. What we call now in India as block marketing. Okay, at an international level. Okay, and that they tried to use for NOAA AVHRR. And another very interesting application of NOAA AVHRR is during Gulf War, Iraq, Kuwait. Okay, that time sandstorms used to be a major issue, and if there is a sandstorm, you cannot fly your aircraft very close to the region. So the sandstorms and their movement were monitored through NOAA AVHRR. Okay, although NOAA AVHRR is actually supposed to be for civilian purpose, these are some places where they are used for strategic purposes. Okay, and they say that during the war, anything and everything will be used only for war, right? So that's the way NOAA AVHRR data was also used. Although it is very coarse spatial resolution, it was used for that purpose. And this 11-bit data is a dream come true for any remote sensing scientist in early 70s, that kind of very high radiometric resolution. Its comparison now, if you want to talk about IRS 1C and 1D, our own remote sensing platforms, we have a sensor called WIFS, Wide Field Scanner, or AWIFS, Advanced Wide Field Scanner. Okay, they are available at 10-bit radiometric resolution. They are now replacing in the recent past to talk about agricultural drought assessment. Okay, that's the way this satellite has played a big role, and now IRS 1C and 1D are also providing this information. Just to give you an idea, if you see a 2-bit data on the left hand side for the same region, this is an 8-bit data for the same region. Okay, so 2-bit data will be coarse, so you will not be able to see many features on the image very clearly, whereas they are available crisply in this image. Okay, so typically the more the radiometric resolution that you have, the better would be 1 pixel's information content, whatever may be the spatial resolution of that particular satellite. Okay, and that plays a very big role. Last important characteristic that I want to talk to you about is called temporal resolution, and this is unique only to satellite remote sensing. If you talk about aerial remote sensing, what happens is we fly aircraft whenever we want. So you may fly aircraft today, and you may fly aircraft tomorrow, and you may fly after 1 year. Okay, whereas when you talk about satellites, by nature they orbit around the Earth. I always show Earth is in my hand. This is Meri Mutti mein. Okay. And then if I talk about a satellite orbiting like this, okay, what happens is if the Earth is rotating, it is taking about 24 hours to rotate, okay, and if the satellite is taking about, let's say, 1 hour or 2 hours to rotate, okay, by the time it completes one rotation, Earth would have rotated some fraction, right? So it is observing a newer segment, again a newer segment, again a newer segment. Satellite is always orbiting like this only. It is not changing its path. It is orbiting like this only because of the Earth's rotation and its relative speed. Okay, Earth is taking about 24 hours to complete its revolution, whereas satellite is taking just 100 minutes typically, polar orbiting satellite. Okay, so it is covering newer and newer segment. Therefore, there is a scope for a satellite to cover the entire globe in a given time, and that time is referred to as temporal resolution. Okay, typically it is measured in days. So if we talk about a satellite's temporal resolution being 20 days, it means that if it has observed Bhubaneswar today, okay, after 20 days again it will observe Bhubaneswar. Okay, it would have covered the entire globe within the 20 days, and therefore it will be covering Bhubaneswar again. That means using that particular satellite for every 20 days, you can get an image of any region of your interest. That is a big deal as far as change in a given location is concerned. So if you want to talk about change, any dynamic change that is taking place, we can try to monitor it using temporal resolution, like change in land use, land cover, temporal variation of any feature. And when we talk about our hydrologic portions like monitoring of a cyclone, flood, or any other natural disasters like volcano, earthquake, okay, what we try to do is very simple. We try to acquire an image before the event, acquire an image immediately or during the event if you are lucky. Okay? And if you have that image, you compare these two imageries and try to see what is the change that is taking place. And that is a big advantage that comes to you to temporal resolution. And just to drive that point home with our flood as one implication or variable that's of interest to us, you know, what you are seeing here is Mississippi River and its course. Okay, and during this is non-flood period. Okay, and for the same area during the flood period. If you compare these two imageries, okay, then you can notice that, you know, the river course is like this. Okay, and there is a bridge here, and there are some bridges. Okay, and if you compare that with this image, you can see that this entire area is now flooded, and this entire area is flooded, right? You can see a lot of flooded area, and you know, if you are flying over that region, and if you are just seeing down through the window, okay, this is the way you see it. These are called true color composites, or in the entire visible region only, you have 3 spectral bands and you produce this true color composite. This is from Landsat TM. When compared to that, we can also do remote sensing in near infrared, middle infrared, and if you do that and produce a standard false color composite for the same region, okay, and this is before flood and this is after flood. And as you recall, whatever you see in red color in a standard false color composite is healthy vegetation. It may be a forest area, it may be agricultural area. Again, if you see a red color with a regular shape like rectangle or a square, it must be cropped area, and if it is an irregular area, it must be forest area or natural grass, right? So we shall be able to identify what is the portion of the area that is under crop, okay, and what is the portion that is under industrial area, urban area, and so on and so forth. Okay. Again, I repeat this. Look at this image and look at this image. Okay, and you say that this is water body. Okay, and you count the number of pixels that are there in the water body. Let us say that pixel spatial resolution is, for the sake of simple illustration, 10 meters. Okay, so if I find that there are about 10,000 pixels containing this water body from this point to this point. What is the area of water spread area? 10,000 into 100 square meters. That is the total area under water spread when there is no flood. Are you with me? Now come to this image. Okay, and in this image, now again count the number of water pixels. Okay, because there is a flood, you will have lot more number of pixels. Say, for the sake of argument, you got 50,000 pixels now. From those 50,000 pixels, 10,000 pixels are already there even when there is no flood. So remove that. So you have 40,000 pixels. 40,000 pixels multiplied by 100 square meters is the total area that is under floods now. Are you with me? Okay, so that is the total flooded area. But what we can also do now is out of those 40,000 pixels which are under flood, okay, now look at how many number of pixels. This is entire area is flooded. Now within this, how much area is agriculture? Count the number of pixels which are under flood water, but they are agricultural area. So let us say out of 40,000 pixels, 15,000 pixels are under agricultural area. So 15,000 into 100 square meters area is cropped area which is flooded. Okay. In the same way, if you look at this urban area, count the number of pixels, you can say that much area is under floods. And you look at the industrial area and say that much area is under flood. What we are doing is we are utilizing two important characteristics here. Okay. First of all, the spectral remote sensing, that is multispectral resolution imageries, so FCC, standard FCC, and the spatial resolution of the satellite, because of which we talk about the pixel size and square meters, etc. And third one, the one that I am trying to talk about, temporal resolution. Before the event, after the event. You look at that, you should be able to get the information. Extract as many important statistics as you want. Entire flood inundated area information statistics can be obtained. So we are trying to use the land use land cover information here. We are trying to use the spatial resolution of the satellite here. Okay. We are trying to use the temporal resolution of the satellite and also spectral resolution of the satellite. Of course, radiometric resolution comes into picture because for a pixel, you are talking about the spectral reflectance in various levels, 8-bit, 7-bit, etc. Is that clear? Just to drive that point home again, the implication or importance of temporal resolution, okay, you can see this slide. Trust me, there are about 24 satellite imageries here. Okay. So what you are seeing here is that this entire Krishna river basin standard false color composite, okay, bi-monthly product, Jan, March, May, July, September and November. Every 2 months, what is the change in Krishna river basin within 1 year itself? You may have Kharif crop, you may have Rabi crop, you may have perennial crop. Okay, all those things will be visible to us now. If you look at Jan, especially if you look at March, okay, there is hardly any red tone here. Okay, and that further reduces by the time you come to May. Okay, and whatever you are seeing as red here is actually forest area, evergreen forest area. Therefore, it is always red. Even in the summer, there is some vegetation there. But by the time we come to July, okay, crop growing season, so many crops are seeded. So you can see that there is some red tone happening in large portion of the command area. And by the time we come to September, the peak of Kharif season, okay, you can see large area is red color. Okay, so you can see that large amount of area is under agriculture. It may be rain fed or it may be irrigated, but large area is brought under irrigation. Okay, and by the time we come to November, a large portion of the area is harvested, so red tone again reduces. Okay, and you can talk about Rabi crop here, and Rabi crop is also harvested. So any seasonal change on a bi-monthly scale, if you want, you can also do it on a weekly scale, fortnightly scale, and try to see what is the change that is taking place. That is facilitated through the temporal resolution of the satellite. So that's why we look for what is the temporal resolution of the satellite. Again, if I talk about my particular example that I have given you, NOVA AVHRR, I repeat its characteristics. NOVA AVHRR has a spatial resolution of 1.1 kilometers, has a radiometric resolution of 11 bits. Okay? And if we talk about spectral resolution, it has about 5 spectral bands. All good. One more important characteristic, temporal resolution. Temporal resolution of NOVA AVHRR is 1 day. Means it covers the entire globe in 1 day, and again it covers the area of your interest next day. Okay? It's possible because the spatial resolution is very coarse. So in one image itself will cover a large portion of the globe. Okay? In 1 day it will cover the entire globe. And then it will cover the next day again the same area. So every day you can try to get the information of any region of your interest through NOVA AVHRR. Okay? And that's a big deal as far as, that's why that particular satellite data was used as far as agricultural drought monitoring is concerned in our country for more than 2 decades, almost 3 decades. That was the only source of data for agricultural drought monitoring. We used to call that project as NADAMS, National Agricultural Drought Management System. Okay? So that's the way we got the advantage of temporal resolution of a given satellite. This is applicable only to satellites. If it is an aerial remote sensing, you decide the date on which you want to fly an aircraft. Okay? So it is not fixed. Okay? Now, if you want to talk about the next tool, this is about remote. See, I always request, tomorrow you may be using remote sensing information. While you are using it, please try to pay attention to these 4 characteristics. Okay? Spatial resolution, spectral resolution, radiometric resolution, temporal resolution. Only then that image will make any sense to you. Okay? Otherwise, if you don't know the, let us say, radiometric resolution, a DN of 120 does not mean anything. A DN of 120 in a 7-bit data is a very high reflectance, whereas the DN of 120 in an 8-bit data is just 50% reflectance. Okay? So you should always remember what is the spectral resolution and radiometric resolution of any given sensor. Then only it will make a sense to you. So please pay attention to these 4 important characteristics before you start using any remote sensing imagery. You might have been exposed to a large number of imageries, but please do pay attention to these 4 important characteristics. Now, the next tool that I want to talk to you in my own style is GIS. Okay? And for this, I always take about 5 minutes detour to explain what is GIS in a very simple layman terminology. All of you must be knowing Microsoft Excel. Okay? Many of you are teachers. So what happens is, let us say that you are teaching a class of about 100 students. Okay? And for the subject that you are teaching in a Microsoft Excel, you enter their roll number, their name, and the marks, right, as 3 different columns, right? And when you do that, if you want to know who is the topper, what you should do? You should sort the marks column in ascending order or descending order. But if you sort the marks column alone, the highest marks will go to some other student, right? So while you are sorting the marks column, you should also keep as a key the name column or the roll number column, and they should also be sorted according to the marks, right? If you want to call that as DBMS, Database Management System, right? Now let us say that your college has about 5 branches. Okay? Same subject is being taught in 5 different branches. Okay? For each branch, now what happens? You will have separate Excel sheet. Okay? Then you want to know who is the topper among all the colleges together. Again, your column is marks column. Your attributes are the name column or the roll number column. Okay, but what you are doing now, you are trying to sort this among multiple spreadsheets. You call that as RDBMS, Relational Database Management System, simple way. Okay, now among that RDBMS, you have one of the attributes corresponding to the location. It is GIS, Geographic Information System. Okay, so one of the attributes, any one, at least one attribute should be spatial location. Spatial location can be x coordinate and y coordinate, or latitude and longitude. Okay, and then you can talk about that RDBMS as GIS. Geographic is that XY coordinate or lat long. So Geographic Information System. Now, if you want to talk about GIS, Geographic Information System, give me any feature on the ground, on Earth's surface. Okay, we can try to represent that either as a point, line, or polygon. This is also known as feature-based GIS. Okay, so if you want to talk about that, for example, a Survey of India benchmark or a railway station, okay, that could be your point, whose XY coordinates or whose longitude and latitude are available to us. Okay, that's a point information. If you have, let us say, a river network, a river like this, or a railway line, or a road line, or canal line, okay, you can see that there is a line, there are lines. There is no line here, it's actually curve. But what is happening is, this is one line, this is another line, this is another line, this is another line. All these lines put together will make it a curve. Okay, so this is line. Third one is small difference, line only, but the point where you are starting is the point where you are ending. It becomes a polygon. If you are starting here, that line will finally come and close here. Polygon or an area. Okay, so it's like a lake or a watershed or Bhubaneswar boundary, Bhubaneswar city boundary, anything like that. Okay, that could be polygon. So give me any feature on our surface, I can either be able to represent as a line, point, or polygon. Okay, as far as our hydrology is concerned, if you want to understand that portion, you can see that for a given watershed, there are 5 layers of information that I am trying to show you through GIS. Each layer has only one particular feature, point, line, or polygon. If you look at the first layer of the same watershed, all these are referring to the same watershed. Okay, first layer is about land use, land cover, polygon. Okay, so for example, this is, let us say, urban area, this is a water body, this is an industrial area, this is a park. These are different land use, land cover categories. Each one of them are shown through a polygon. Okay, so polygon is the feature that is representing this particular layer. And if you look at the next layer, soil type, this is black cotton soil, this is red laterite soil, this is laterite soil, and so on, again represented through polygons. Okay, now within this polygon, let us say that we have a stream, and on that stream these yellow dots are the gauge stations where you are measuring the stream flow, and those gauge stations are point information. Provide the latitude and longitude for that, we have the point information. So gauge station is shown through point information. Okay, and if we talk about the stream, its watersheds, then you can see that they are all different polygons. So large number of features that are available for a given watershed, each feature can be a point. Okay, that's the way you can represent any number of features on Earth's surface through GIS, multiple layers. I think you might be knowing about this diploma in civil engineering, and before that there is something also called a draftsman, ITI. Okay, and there used to be something called cartographer or a draftsman, right? And they also used to do it on tracing sheet. Yeah, Okay, that what that cartographer or the draftsman used to do, we can do it now through remote sensing. What he will do is, he will take your rough sketch of a plan of a building, okay, and he will draw a beautiful, perfect to the scale, a map, plan, front view, back view, everything, sectional view, all those things, cross-sectional view, all those things are generated by that particular draftsman. Same thing, GIS can do it now for us. Okay, and in this context, we also use one more terminology very frequently in GIS called query-based analysis. The query-based analysis is using these all multiple layers of imageries. Please tell me how many number of stream gauges are there in which my soil type is black cotton. That is a query. That is a question that we are asking. Okay, what is the question? I want to identify those stream gauges which are within black cotton soil type. Okay, so if you look at, then what we should do is, we should look at the stream map, we should look at the stream gauge map and the soil map. If we put these two layers together, okay, so let us say this entire thing is black cotton soil. Within this black cotton soil, if I have any yellow dots, those are the gauges which are there within black cotton soil. So to answer that question, we don't require all these 5 layers, but we require this layer and this layer, and this in GIS terminology is also known as drill down technology. The main advantage why I am trying to talk about a draftsman is that draftsman always draws his figures on a tracing sheet, transparent sheet. Okay, here all these layers are transparent to each other. So you can stack them in any order that you want, but they are transparent to each other. So you can see one below the other. Okay, that's the advantage. I don't know if you have done some kind of a manipulation in engineering drawing course examination. We used to call that as glass tracing. Yeah, if you haven't done it, you are not a good BTech student. Okay, so that, I mean, you don't teach that to your students now. You'll say, make sure that they won't do that. Okay, but you know how to do it, right? So that glass tracing is only between 2 sheets. Here you can do it for multiple sheets, as many number of layers if you want. You can stack them and try to do the analysis. Just to give you an idea, you look at this, is a very interesting picture that is shown very often. Okay, this is playing with nature. That is the name of this cartoon, playing with nature. Okay, what is done here is that, look at this rectangle. Okay, same rectangle in all these layers. Okay, same area, same spatial resolution, same spectral resolution, same radiometric resolution. Okay, only thing is, it is showing different features. If you look at the first map, this map says that, I am trying to use all these layers to go for urban development in a given region, say Bhubaneswar city. Okay, I want to decide where I should focus on urban development. Okay, now this first map tells me that this portion that is there in black color is not suitable for urban development because of the type of soil that we have. Maybe it's a wetland or whatever it is not suitable as far as urban development is concerned. Okay, now if you look at the second map, this is a map showing the parks. Okay, now in this map, okay, so put all these 4 layers together, stacking. Okay, then you get an image like this. But it is drill down technology. Multiple layers of information will be able to utilize for that. Any question? I told you, if you ask me questions, I will be the happiest guy. Okay, so if we try to use this GIS technology now, what we can try to do is, if you see these layers of information, we can try to use GIS as far as the water resource assessment is concerned in various portions of the domain. Okay, first one is that in database development itself. Okay, we can have collection, processing, inventorying, hydrologic, hydroclimatic, hydrogeological, and auxiliary data. Try to put all of them together. We create data and we try to answer questions like, first of all, what is the rain gauge location? Means you need the XY coordinates our units need its latitude and longitude. If we specify that, we know that dot, where the dot sits in the map. Okay. And the same way, if you have, let us say, stream gauge, you have, let's say, another meteorological station. Okay. All of them, we are trying to create a database in GIS framework, as many number of layers of information as you want. And the advantage with this kind of thing is that I told you that I require only one spatial attribute. So if you talk about a rain gauge, that rain gauge may have about 20 years of daily rainfall, 20 into 365 numbers, all for one location. That is temporal database. Okay, all that can be stored very effectively in GIS. And then the first thing that we do, let us say that we have about 10 rain gauges in a catchment. If you want to find out what is the representative rainfall of the entire catchment, what we'll do? 3 methods that we teach to our students. Arithmetic average. Excellent, right? So Thiessen polygons, you draw perpendicular bisectors and all, GIS can do that for you. Okay. Even the industry benchmark open source GIS software like QGIS, there is called Werner polygon algorithm that is available in it, which can try to draw Thiessen polygons if we just provide the rain gauge locations. Okay. In the same way, what are isoheights? Isoheights are basically the contours joining the equal amount of rainfall. Yeah, right. So that we can try to draw it again using GIS. So that is interpolation, technical information extraction, interpretation of data of hydrologic for hydrologic modeling and regionalization can be done. Topological, network modeling, cartographic modeling, map overlay, geostatistics, all those things can be done through remote sensing. And the last one is actually knowledge decimation or information extraction. Again, for that, one of the best examples that you use every day is your Google Maps. Okay, the moment you get into your car, first thing that you do is, you mention the destination, and it will show you the path that you should take, but it will also show you in red color the portions where you have a lot of traffic density. Right? All that is through GIS, and the information is disseminated through online portals to your mobile or any other handheld device. Your mobile itself is not doing any computing. GIS platform or the server is doing that, but is providing the end result to you through GIS. This is very useful when you talk about visualization and also information extraction. So GIS again plays a big role, and in that we also talk about decentralized databases. For example, within a river basin, if you have, let us say, 5 major controlling authorities of water resource department, okay, each portion controlling a small segment of the basin. That information is put on a cloud or on a GIS platform or a GIS server and analyzed, and you try to get the total information of the entire basin. Okay, and that is done through knowledge extraction or knowledge decimation. Yeah, geostatistics is as simple as, let us say that I have about 10 rain gauges in a basin. Okay, for every pixel, I want to know what is the rainfall in that pixel. How do we do that? If we use Thiessen polygon method, okay, for those 10 rain gauges, we construct polygons, and finally we'll have 10 Thiessen polygons covering the entire basin, indicating that any polygon comprising of one particular gauge station, rainfall in that polygon is exactly same as what is recorded in the rain gauge, right? That means every pixel's rainfall value we know now. Okay, and using that, if you use our unit hydrograph theory or something and try to get what is our effective rainfall, okay, effective rainfall multiplied by pixel spatial resolution, okay, you get what is the total volume of runoff. That is a geostatistic that we are extracting from the rainfall data using our geospatial statistics to get what is the total volume of runoff that we got, okay, for the entire basin, pixel by pixel. Okay, like the way we calculate the number of pixels under flood water, and the number of agricultural pixels under flood water, like that. Those extraction of statistics saying that this much area is under agricultural, that is flooded, at this much area industrial, it is under flooded. The extraction of statistics is called done through geostatistical tools. And it's not that, I'm just giving a simple example. We can also use it for interpolation. For example, let us say that in one location the elevation is this much, and in another location the elevation is this much. Then what we do for our surveying, we try to do interpolation. Okay, linear interpolation, spline, nth order polynomial. Okay, all those are geostatistical tools. Okay, that's a way we can try to utilize geostatistical tools. Map overlay I have already explained to you in detail. Okay, so all that can be done. So this is one more tool that I want to talk to you about, GIS. Okay, and this GIS plays a big role, and I'll explain all these tools. Finally, I'll take everything and put them in water, because I'm a water resource guy. Okay, so we'll try to utilize finally all these tools in water resources. But right now, I talked about two important tools: remote sensing and GIS. Okay, and after coffee break, I'll talk about DEM and then utilization of all of them in hydrologic models. Thank you. Will we start? Okay. So as I recall, I took my own time to explain two important tools, remote sensing and GIS. Okay. Now I'll try to use these two tools to talk about what we can do with these two tools together for flood monitoring. Okay. I'll try to take that through one case study, which is not a good case study. It's a disaster. Flood is always a disaster. Okay. So about how we try to monitor a flood, which is actually kind of a man-made flood, okay, and what are the implications of it. Have you heard of this famous or infamous flood event called Kosi River breach? Okay. Now I'll spend about next 10 minutes only to explain about this particular flood event. Okay. And this is a very interesting feature as far as remote sensing is concerned, remote sensing GIS are concerned, to such an extent that United Nations also has sponsored lots of studies on this particular event that took place sometime in 2008. Just to give you a context, this is the Kosi River. Okay, it originates in Himalayas, flows through Nepal, okay, and reaches Ganga here. Okay, Bihar, Jharkhand, and other places it flows through. In case if you have heard about Kosi River, if you are from Bihar or Jharkhand, you would have heard this name, that Kosi is known as sorrow of Bihar, because it causes so much of floods every year. Okay, so this particular event that I am trying to explain has happened in 2008. In this image, satellite imagery on a standard FCC, look at this small portion, this circle that is shown here. Okay, that's the place where, due to heavy flood, okay, there was a breach in the river bank. Okay, and that breach is so big that river itself has changed its course. So the river that is supposed to flow like this and reach Ganga, okay, has started flowing like this and reach Ganga. So imagine those people who are living here, they don't even expect one drop of water to flow through them. Now suddenly a mighty river is flowing through them. Okay. That's the main issue that has created problem as far as this particular flood is concerned. This is popularly known as Kosi River breach problem. I'll try to explain this in two important categories. One, in terms of multi-temporal resolution satellite imageries and GIS. We try to utilize both of them to understand how this breach has taken place and how it has propagated from this place up to this place. Okay. So you remember, this is the original course of the river Kosi, and this is the new course of the river after the breach. Okay. Let us focus first of all on this small circle. Okay. If I want to focus only on that small circle, what I should do is that I should go for a very high spatial resolution image. Okay. So what you are seeing here is that high spatial resolution from LIS4 data from IRS or Cartosat data from IRS. And these satellites provide the information at less than 5-meter spatial resolution. So that circle alone is this image now. The small circle alone is this image. And the Kosi River original course is like this. And if you look at during the breach, okay, the river, instead of flowing like this, there is a breach here, and river started flowing in this direction. When we talk about a canal breach or a river breach, the breach length, we try to measure in meters, right? But here, the breach length is 1.7 kilometers. Okay, such a large breach has taken place there, 1.7 kilometers. Okay, and you can see that this is the original course, and the river has changed course through this breach location. And look at this small structure here. This is a civil engineering man-made structure called SPUR, S-P-U-R. Okay, I will try not to talk much about it because I don't want to demean a civil engineer. Okay, so if you talk about this Kosi River, okay, this is the way the flood has taken place. That is as far as the small portion is concerned. But now let us look at this entire region from here to here. If we have acquired imagery from any particular satellite during this event, there is one United Nations consortium. As per that, if there is a flood happening in any given location, any satellite of any country, if it is passing through that region on that day, you can request for that image from that satellite. It is freely shared. You provide the data same way from our IRS program to other countries, and they provide the data to us. So we acquired as many number of satellites as possible and try to look at how the progression of the flood has taken place through this breach. Okay, so these are all, you see it as one innocent map here, but trust me, there are about 36 layers of GIS on this multispectral images and lot of spatial locational information. Okay, so if you look at on 20th August 2008 satellite imagery, flood water, the total length from here to here is 120 kilometers. Okay, so flood water has progressed by 60 kilometers. That means half the distance it has traveled by 20th August. By 22nd August, it traveled another 35 kilometers. So 60 plus 35, 95 kilometers. Okay, and by 24th August, it traveled the total distance of 120 kilometers. So it took some time to reach this place. One more point that all hydrology or hydraulics concepts that if you remember, Q equal to AV, right? So if you have some discharge taking place in this river and the same discharge has to take place through this river, there is no river here, there is only plain land. Okay, so what happens here, there is a lot of depth of flow. Okay, so it can carry more amount of discharge. Same discharge, if it has to be carried in a narrow depth, what happens? Width has to be more to carry the same discharge, because Q equal to A into V, and A you can either increase either depth or width. Okay, here the depth is less, so width has to be more. And river width we typically measure in meters, unless it is a Mahanadi or Brahmaputra, right? So if you talk about the river width here, 13 kilometers. I'm not talking about the length, I'm talking about the width. And here it is 25 kilometers. Here it is 37 kilometers. Okay, so when you don't expect a drop of water to flow through you, a river of that much width is flowing through you. Okay, it causes major devastation and huge amount of life and animal life, human life and animal life is lost in this. You look at the districts. Okay, by this time Saupal district is flooded, and by this time Madhepura district is flooded. Districts, not one village or something like that. Okay, and Sahasra district, Saharsa district, and other places, entire area, Kagia district, everything is flooded by the time you reach here. Large amount of devastation took place because of this event. Okay, and that's one important aspect that is studied through two major tools, remote sensing and GIS. And in hydrology, you would have had one more name. The river changes its course. What is it called? Meandering. Okay, meandering of the river can also be monitored through remote sensing, because remote sensing data is available for decades. Okay, so look at the decade back imagery and look at the current imagery, compare the river course and see what is the change. Therefore, you can talk about meandering. Let us look at this small portion again, this small circle here. Okay, everywhere that you are seeing the circle. Okay, let us focus only on that on a decadal time scale. Okay, so what you are seeing here is a few decades of imageries. Okay, that's again the multi-temporal resolution satellite capability. So this is 1998 imagery. Okay, this is 2001 imagery. Both are in the same season, August. Okay, now look at these two imageries first of all. They are actually simply gray tone imageries. Okay, this is from microwave remote sensing called RadarSat satellite. Okay, you look at these two imageries and look at this section. This river is flowing like this. Kosi river is flowing like this. Okay, look at this section A. Okay, and see the width of the river. This is the width of the river. Okay, river is flowing like this, so you call this as left bank and you call this as right bank. Okay, and just 3 years down the line, in the same August, okay, look at the river cross section. Okay, there is little flow on left bank, there is a lot of flow on right bank, whereas here it is almost there for the entire cross section. Okay, what happened? There is a lot of flow that is now on the right bank. Assuming that the discharge here and here is same, cross section has reduced, that means velocity must have increased. Again, Q equal to A into V, right? So velocity must have substantially increased. Look at this one. Again, a cross section. At this one, what is happening? You hardly have any flow on the left bank and lot of flow on the right bank. Look at this portion. There is hardly any flow in the right bank, but all the flow is on the left bank, and that too very narrow width. Same discharge has to be carried here with high velocity. Although river course is like this, as far as A to B or A to 1 is concerned, river direction is like this, dotted line or dashed line. With such on the dashed line, river is flowing with very high velocity. It is coming and hitting this bank, and then it is changing its course. What happens to this bank? It gets eroded. That's the place where the breach has happened. Okay, the river is meandering, and that meandering has caused so much of stress on this bank, and that's the place where the river bank got eroded, especially during flood, and therefore you had a breach. This is the same thing. You can see that this 2 location is the place where the breach has taken place. Okay, and you can see it further amplified. These are all in the same period immediately after the event in 2008. Okay, so river meandering also has contributed substantially, apart from the heavy flood waters, to cause the erosion and the riverbank breach. Third one that caused is that spur that I have shown you. Okay, this spur. It is changing the river. This is river engineering work. It has changed the river course to focus more on this portion of the bank. Okay, all these 3 together have caused this major disaster called Kosi River breach. Okay, it's a bad event, but my intention here is to explain the aspects of remote sensing and GIS and their role as far as flood monitoring is concerned. I'll explain again in some other terms in my afternoon session also, because I'll focus a lot on floods. Okay, but before I do that, I want to talk about one more tool which you already seem to have been exposed, but again I'll expose you through my own way of doing it, okay, called digital elevation models. Yeah, there is a scope to all the study that you are seeing here with some attribute to this person. Okay, this was done after the event. This is like called a post-event, post-mortem analysis. Yes, we can get it. We can get it as long as you have one satellite that is passing through that region on that date, 1 day before the event, 2 days before the event. If you have a satellite passing through that, we have the image and analyze that image. We know what is exactly the situation before that event. Through NRSC, nowadays we don't have to do that. Actually, we conduct lots of tutorials on that also. Use one website called Earth Explorer. Okay, and there it's a US GS. I'll send you the link and other things by email. Cipra will send it to all of you. Any satellite imagery for any date, for any location, you can download freely from this website. Okay, and there are 2 or 3 such websites. The one that I will send you is very useful. Okay, you don't have to worry about how to place an order for it. Go to world map or go to India map and draw a rectangle around the region that is of interest to you. Okay, and that it will note it as latitude and longitude, and try to search any satellite image of any satellite, okay, and see whether that data is available. So it will say that on this date this satellite image is available, on this date this satellite image is available. It may not be one image because of the rectangle that you have drawn. So it may be more satellite images will be required. It will put all of them together and say that you have to download all these imageries. No, it is generally available within after 1 week of the imagery acquisition. So after 1 week you will get them, not immediately after 1 day. Sometimes what they do is they make it commercial. That portion they try to sell. 25,000 rupees I told you, no? That's where they will sell. But afterwards they will make it freely available. Even very recently, just Government of India has had a open source system. Government of India signed a big document. As per that system, any geoinformatic data that is available from any Indian Space Agency must be available to large community within India, especially the academic community. So it will be available. If you want to look for that, look for Bhuvan website, BHUVAN, or Bhumi website. That's updated every fortnight. And that too, the problem with that is that they will give the end product. That means they'll directly give the land use, land cover map, but not the original satellite imagery. Whereas from the other website that I'm mentioning to you, you get the satellite imagery, you can do whatever the analysis that you want to do. Both are available. Okay, so this one also I'm going to talk about. Again, this is also freely available data. I'll talk about that little later. But typically, this is what we see through digital elevation data. Like the way I talked about GIS, I'll take 2 minutes to talk about DEM in a very layman terminology. In your surveying course, using dumpy level or total station, you would have obtained elevation of a given location. What you will do? You will use your chain survey or something and try to identify the location, and at that location you put your staff gauge, okay, and get the level through your dumpy level or total station, and convert that to reduced level or mean sea level. Okay, that means what? For a given location, we know what is x coordinate, y coordinate, and the z coordinate or z coordinate, right? Are you with me? Okay, x, y, z coordinates. Now that data has 3 columns. If you try to store it in computer, it will become digital elevation data. You play around with it, it will become digital elevation modeling. Next 15 minutes, we play around with the digital elevation data. Okay, 15 minutes upper limit. Okay, so if you try to look at that, see what you are seeing here is actually the 3-dimensional feature to show the elevation. You know, you would have heard, you know, what is this red line is called? Beautiful. Watershed boundary or ridge line. What is the definition of basically of ridge line? Ridge line is a contour of highest elevation, right? So what is the importance of ridge line? You already talked about watershed also. Okay, if the rainfall is occurring in this entire image area uniformly, okay, rainfall that is occurring within this ridge line will flow into this. Anything outside this ridge line will flow away from the ridge line, right? The ridge line itself is a contour that you can draw using your dumpy level or total station. You have done it in your BTech coursework, right? Or you teach now to your students, right? So if you do that, this is our ridge line. And can you see this brown line? Okay, this is also a contour, but this is a contour of lowest elevation, which is called as valley line. Okay, so if there is a rainfall in this entire ridge line region, all the water will finally get collected into this brown line portion, and through valley line water will flow. So as far as the digital elevation data is concerned, it is extremely useful as far as the hydrology or water resource planning and management is concerned. We shall now try to utilize this. What we did is that we have x-axis, we have y-axis, and we have the z-axis showing the elevation. The height of each box is the elevation at that location. Okay, so we can try to visualize this three-dimensional surface, and you would have done in your surveying also that you try to do interpolation between 2 points. The elevation at one point, the elevation at another point. Between those two, you try to do the linear interpolation, or you can try to put a spline or any type of nth order polynomial if you want to do, and draw a smooth curve. Okay, when you drew a smooth curve, you can try to visualize the three-dimensional surface, and that surface you can visualize. You may have more number of triangles in a small region. That means you have more amount of elevation information available, and in some places you have sparse triangles. Try to do all this.